Olympiad-level geometry is tough? Well, an AI just got insanely good at it. So good it might start coaching human contestants. Meet AlphaGeometry2, the latest math whiz on the block, and it just made a huge leap in performance. The first version is already pretty solid. It could tackle 54% of IMO problems, but version 2 is solving 84%. How did it get so smart? First, the AlphaGeometry language got a major expansion, learning to handle moving objects and linear equations. That means it can now understand way more types of IMO problems, going from 66% coverage to 88%. Then, it leveled up its search process with the Gemini architecture and a knowledge-sharing system where multiple search trees team up to find solutions faster. So how did AlphaGeometry2 get this good? Let's dive in.
Let's dive into AlphaGeometry2, the next-gen version of AlphaGeometry, designed to tackle Olympiad-level geometry problems with even more power. You might remember its predecessor, AlphaGeometry1, which was already impressive. But AG2 takes things to a whole new level. It expands the system's language to handle harder problems. Think object movements, linear equations of angles, ratios, and distances. This upgrade alone boosted its problem coverage from 66% to 88% for International Mathematical Olympiad or IMO problems from 2000 to 2024. But here's the real game changer: the search process. A G2 uses the Gemini architecture, which gives it a smarter language model. This lets it navigate proof searches more efficiently. Plus, it introduces a knowledge-sharing mechanism where multiple search trees collaborate. Combine that with upgrades to its symbolic engine and synthetic data generation, and you've got a system that now solves 84% of problems. A massive jump from 54% before. And it's not just about numbers. A G2 was part of the system that reached silver medal performance at IMO 2024. The long-term goal? A fully automated AI that can solve geometry problems directly from natural language descriptions. Imagine that, human-level theorem proving, powered by AI. Now let's talk about the IMO, the International Mathematical Olympiad. It's one of the toughest math competitions for high school students. The problems require deep conceptual understanding and creative thinking. And among all the categories, geometry is often seen as the most structured and approachable. Over the years, researchers have tried two main ways to automate geometry problem solving. One is algebraic, using methods like Wu's method or Grubner bases. The other is synthetic, which is more human-like, relying on deduction databases and full-angle methods. The synthetic approach is often more adaptable across different domains. AlphaGeometry1 was a hybrid system, combining a language model with a symbolic engine. It solved 54% of IMO geometry problems from 2000 to 2024, a big step forward. But it had limitations. Its language was too narrow, its symbolic engine wasn't efficient enough, and its language model struggled with problem variations. Enter AlphaGeometry2. It's powered by a more advanced Gemini-based language model, trained on a bigger, more diverse dataset. The symbolic engine has been upgraded too, with a leaner rule set and better handling of complex cases like double points. The domain language now covers more geometry concepts, including locus theorems and linear equations. These improvements make AG2 a much stronger solver, pushing the limits of AI in mathematical reasoning. So how does AG2 build on its predecessor? One big upgrade is its search algorithm and knowledge-sharing capabilities. It can explore a wider range of geometric constructions and uses Gemini AI to convert natural language problems into structured geometry representations. This makes AG2 more autonomous, bringing it closer to a fully automated reasoning system. Another key improvement is its ability to handle a broader set of geometry concepts. A G1 relied on 9 predicates, predefined rules for recognizing relationships like congruent line segments or perpendicularity. These were enough to solve about 2/3 of IMO problems, but they lacked flexibility. A G2 fixes this by introducing 2 new predicates, one for finding angles between 2 segments, and another for calculating the ratio of their lengths. These might seem like small additions, but they're game changers. Now AG2 can actively compute missing geometric quantities, making it far more powerful for tackling Olympiad-level problems. A G2 also expands its ability to reason about geometry by introducing new predicates for distances, angles, and movement-based relationships. This lets it process problems involving proportional segment lengths, directional constraints, and specific angular properties, things AG1 couldn't handle. A major upgrade is AG2's ability to tackle locus problems, which involve moving objects like points, lines, and circles. It introduces a placeholder symbol for fixed points, making it possible to express constraints like find the circle passing through 3 fixed points, or find a line at a fixed angle. These upgrades significantly increase the range of problems AG2 can solve. To ensure accuracy, AG2 includes diagram validation predicates. These enforce geometric constraints like clockwise ordering of points, distinguishing between distinct and overlapping points, and handling inequalities in segment lengths. A particularly important addition is the ability to define overlapping points dynamically, meaning AG2 can recognize when points share the same center in a cyclic arrangement. These enhancements make AG2 far more capable of handling real Olympiad problems, going beyond simple fixed structures to reason about dynamic geometric relationships. One of the big challenges in using AI for geometry is converting problems from natural language into a structured format that the model can process. A G1 required manual translation, but AG2 makes this easier with automated formalization. Here's how it works. AG2 uses Gemini AI to transform geometry problems into AlphaGeometry's domain language. Researchers first manually translated a few dozen problems to create examples. Then, Gemini AI was prompted to translate new problems based on these samples. To ensure accuracy, it was run 5 times per problem, and another AI pass merged the results into a final answer. The result? A G2 correctly formalized 30 out of 39 problems with near-perfect accuracy for simpler cases. Another challenge is diagram generation. A G1 could only define points by the intersection of 2 objects, making it impossible to construct more complex setups. A G2 removes this restriction, allowing points to be defined by multiple predicates at once. This is crucial for non-constructive problems, like defining a triangle's incenter with extra constraints. To automate this, AG2 encodes each point's constraints as mathematical functions and then numerically searches for valid coordinates. This allows it to handle diagrams for problems where points can't be defined in a simple, step-by-step manner. It's a major step toward making AI-powered theorem solving fully autonomous. Generating diagrams for complex geometry problems isn't just about drawing shapes. It requires the AI to find valid numerical solutions. A G2 refines this process with a 2-stage optimization. First, it runs a standard gradient descent to minimize errors and constraints. Once it reaches a stable solution, it switches to a more sophisticated numerical method to fine-tune accuracy. This upgrade makes a huge difference. Testing. On 44 IMO problems, AG2 successfully generated diagrams for 41 of them, many within seconds. The remaining ones took longer but were eventually solved using large-scale parallelization. Another major upgrade is in AlphaGeometry's symbolic engine, called DDAR. This system is responsible for proving theorems by iteratively deducing new facts from given ones. Faster data generation means better training for the AI, while a more efficient proof search helps it reach solutions faster. One key issue with the older version was its inability to handle double points, situations where 2 different names refer to the same coordinate, A. A G2 fixes this by allowing the model to reformulate proofs. For example, instead of proving that a point lies on a circle, it can prove an equivalent but easier statement that connects different intersections. This flexibility makes solving difficult geometry problems significantly more manageable. Handling double points is one of AG2's biggest improvements. The problem is that proving a point lies on a circle can be difficult. Instead of tackling it directly, AG2 reformulates the proof by introducing an auxiliary point at an intersection. Then, if it can show this new point satisfies the same conditions, the original proof follows naturally. This trick simplifies a lot of challenging geometry problems. The symbolic engine also gets a major boost in efficiency. A G1 had a slow proof search process because it had to check all possible deductions one by one. A G2 improves this in 2 big ways. First, it hardcodes common search rules so it doesn't need to recheck them each time. This cuts down on redundant queries and makes the engine much faster. Second, it uses hashing to detect common geometric patterns. Instead of blindly checking all triangles, AG2 hashes their shape and only searches for matches when a duplicate appears. The same goes for cyclic quadrilaterals. It hashes key segment values, making it much easier to detect important relationships. These optimizations let AG2 process proofs in a fraction of the time, making it much better at handling complex Olympiad problems. One of the biggest changes in AG2 is the speed boost in its symbolic reasoning engine, DDAR. The original version, DDAR1, was incredibly slow, taking nearly 20 minutes to process a single problem. A G2 changes that by rewriting core computations in C++, making it over 300 times faster. Now, the same problems that took almost 20 minutes are solved in just 3.5 seconds on a high-performance CPU. Another key upgrade is in synthetic training data. Instead of relying on human-crafted examples, AG2 generates random diagrams and extracts all possible geometric facts from them. It then backtracks to identify the key steps needed to prove those facts, ensuring each proof is logically sound. This approach prevents bias from existing problems and allows AG2 to discover new, unexpected theorems. AG2 also scales up dramatically. It works with diagrams twice as large, proves theorems twice as complex, and generates 10 times more detailed proofs than AG1. Perhaps the biggest leap is its ability to handle locus problems, which involve tracking how one point's movement affects another. This was impossible in AG1, but AG2 records movement dependencies, making it far more powerful in tackling real-world geometry problems. A G2 takes a big step forward by significantly expanding the complexity of its training data. Compared to AG1, AG2 deals with problems that have more points, involve more complex relationships, and cover a wider variety of question types. One major upgrade is how AG2 balances training data across different types of geometry problems. A G1 had uneven distributions. Some types of questions had far more examples than others. A G2 fixes this, making sure that categories like collinearity, perpendicularity, cyclic quadrilaterals, and ratios are all well represented. This helps the model generalize better to different problem types. Another improvement is in how AG2 handles auxiliary points. A G1 was biased. 91% of its training examples had no extra constructed points, making it struggle with proofs requiring additional constructions. A G2 fixes this, balancing the mix so that half of its training problems include auxiliary points. Finally, a G2 introduces a formal way to track point movement dependencies. If a point is defined as a midpoint, it depends on two other points. If it lies on a line, it moves along with all points defining that line. This helps a G2 reason about locus problems, where one point's movement affects another. One big challenge in AG1 was figuring out the smallest possible set of points needed to prove a geometric fact. The old approach was brute force. It removed different subsets of points and reran the proof-checking process to see if the result still held. This method worked, but it was painfully slow because the search space grew exponentially. A G2 fixes this with a greedy algorithm. Instead of testing every possible subset, it simply works through the points in reverse topological order, starting with points that don't depend on anything else. It removes a point if the proof still holds without it, ensuring that only the minimum required set remains. Another big improvement is in proof search. A G1 used a single beam search, which explores the most promising options but doesn't always find the best path. A G2 introduces a parallel search strategy where multiple beam searches run at the same time. Even better, these searches share information with each other through a shared facts database. If one search tree figures out something useful, it passes that knowledge along, speeding up the entire process. There's also a new multi-auxiliary search tree, which allows the system to predict multiple auxiliary points at once rather than just one at a time. This expands the search space and helps find better solutions faster. When solving geometry problems with AI, one of the big challenges is turning a natural language question into something the system can understand and prove formally. A G2 tackles this using multiple search trees. First, the problem gets translated into a structured format. One part describes the geometry relationships, and the other handles diagram construction. Once that's done, the system launches multiple search trees in parallel, each configured slightly differently. One search tree follows a classic approach, introducing one auxiliary point at a time. Another tree allows multiple auxiliary points to be introduced together, and a third tree is optimized for certain types of transformations. What makes this system clever is the shared workspace of interesting facts. These are facts that wouldn't be found by the standard symbolic engine, but are discovered through search. Once one search tree finds something useful, it shares that fact with the others, speeding up proof discovery. To make auxiliary point generation more efficient, the system also tweaks how it prompts the language model. Instead of letting the model generate auxiliary points randomly, it forces it to generate specific types, like collinear points, perpendicular points, or cyclic points, so that all possibilities are explored more evenly. This structured, multi-tree approach makes AG2 significantly better at proving complex geometry theorems than its predecessor. By sharing knowledge between different searches, it avoids wasted effort and speeds up the process of finding correct proofs. When it comes to proof search, AG2 operates on TPU-v4 hardware to handle multiple search trees in parallel. Each tree follows its own strategy but queries the same model to maximize efficiency. While these search trees work asynchronously, also runs its language model workers and symbolic engine in parallel. The language model explores possible solutions, stores them in a database, and the symbolic engine picks up those solutions to verify them. Next, the paper introduces a new language model that improves on AG1. The previous model used a two-phase training approach, first on general problems, then on those requiring auxiliary constructions. A G2 simplifies this by training in one phase using a sparse mixture of experts transformer based on the Gemini architecture. The training data consists of about 300 million theorems. 3 different training setups are used: training from scratch with a domain-specific tokenizer, fine-tuning pre-trained math-specialized models, and multimodal training that incorporates images of geometry diagrams. To evaluate the model, 3 test sets are created: one with general problems, another focusing on auxiliary points, and a third featuring IMO problems solved by AlphaGeometry. These improvements streamline both training and inference, making AG2 better at recognizing geometric relationships and proving more complex theorems with fewer errors. Training these models requires careful tuning. G2 uses the largest batch size possible on TPU-v4 hardware, following a warm-up phase before gradually reducing the learning rate. As expected, larger models tend to perform better, with reduced error rates across different evaluation sets. The paper highlights how scaling up from a 51 million parameter model to a 3.3 billion parameter model consistently decreases the loss across training, evaluation, and IMO-specific test cases. Inference follows a different approach compared to AG1. Instead of relying solely on greedy decoding, AG2 uses a top sampling strategy to increase diversity in generated auxiliary constructions. With a low temperature and minimal sampling, the model can only solve a fraction of problems requiring auxiliary constructions. However, increasing the temperature and allowing more sampled solutions dramatically improves performance, solving more IMO problems. This setup is crucial for solving geometric proofs, where auxiliary constructions can determine whether a solution is found. However, using very high temperatures can lead to outputs with incorrect syntax, making the right balance important. A key challenge in AG2 is integrating the language model with the symbolic deduction system, DDAR, to improve proof generation. To achieve this, AG2 introduces an enriched interface, where the language model is informed about what DDAR has already deduced before generating new auxiliary constructions. 3 different sets of facts are considered: basic deductions from problem premises, deductions assuming the final goal is true, and numerical validations from the diagram. These facts are concatenated into an analysis string that the model uses to refine its predictions. The results show a significant improvement in solving IMO geometry problems. Out of 50 formalized problems, AG2 solves 42, exceeding the performance of previous methods and surpassing the average score of a gold medalist. The solve rate increases with more training tokens, as shown in Figure 7. Even with just 250 training steps and a relatively small batch size, AG2 already solves 27 problems. Interestingly, even without a language model, a G2's symbolic engine alone can solve 16 problems, highlighting the effectiveness of its geometric reasoning system. The team also performs ablation studies to examine how different inference settings impact performance. AlphaGeometry2 has made significant progress in solving complex geometry problems. Look at Figure 8 here. It presents a visual breakdown of how AG2 performed on 2000 to 2024 IMO geometry problems. The color-coded grid highlights the problems solved by AG2, those solved by its symbolic engine, and those that remained unsolved. The results show AG2 outperforms previous iterations and surpasses human benchmarks in competitive problem solving. Now check out Table 4. It compares AG2's performance with other AI systems and human scores. The results are striking. A G2 in its best setting solves 42 out of 50 problems, outperforming an average gold medalist, even without the language model. AG2's symbolic engine alone solves 16 problems. The comparison also includes other AG models, such as OpenAI's system and Thang geometry, but none match AG2's overall performance. Interestingly, the results suggest that increasing beam search size beyond a certain point does not improve performance. The best configuration appears to be a beam size of 128, a depth of 4, and 32 samples. Additionally, while AG2 solved most of the problems, 6 remain unformalizable, and 2 were attempted but not solved. Experts reviewing AG2's solutions even noted signs of superhuman creativity, an intriguing claim that raises questions about the system's problem-solving strategies. AlphaGeometry2 is a major step forward in automated geometry problem solving. It solves 84% of IMO geometry problems from 2000 to 2024, a significant leap from its predecessor's 54% solve rate. This success comes from 4 main upgrades: a more powerful language model, a faster symbolic engine, an expanded domain language, and a new proof search algorithm. But it's not perfect. Some problems remain out of reach. The biggest challenge is that some IMO problems require techniques like inversion, projective geometry, and radical axes, which aren't part of the current system. Problems involving inequalities and variable numbers of points also pose difficulties. The researchers suggest that breaking problems into subproblems and using reinforcement learning might help close the gap. The paper also hints at an exciting future: a fully automated geometry problem-solving system that takes a natural language problem and produces a reliable, hallucination-free solution. While AlphaGeometry2 isn't there yet, it's a huge step in that direction. The team believes that better formalization and supervised fine-tuning could push the system even further. Thanks for joining us today. Now go enjoy your weekend. Maybe solve a fun geometry problem, or just let AlphaGeometry2 do the hard work while you relax.